Now that we know how to calculate the pH, we can do a little bit more with our equilibrium, and that's where we're heading. Because we know not all acids are created equal, and we know that we can actually measure directly for the pH of a solution. We got tools for that. We can use things like pH paper, gives us a little color, tells us where we're at on that pH scale. We also got pH meters, which are arguably considerably more precise. And so we can actually measure in solution. So we put some stuff in the water, we let it sit, reach equilibrium, and then we can measure in our equilibrium how much hydronium actually came off. Now, up until this point, we've assumed that it split completely as a strong acid, but we know that that is not always the case. Different acids and bases have different degrees of quote unquote strength, different degrees of reactivity. And this has to do with how easily they give away that H, or to what extent they dissociate. And that is an equilibrium. pH scale, we've seen this before. A lot of household materials that are acidic, as you get closer and closer to muriatic acid, that's our hydrochloric. We get really, really acidic, very, very low on the pH scale. A lot of our cleaning products that clean up fatty acids are bases. They are very much on the alkaline side, or the base side, higher than 7 on that pH scale. Real quick, here's tie into the real world. Acids and bases. But keep in mind, there's kind of two factors that determine reactivity. One of them is concentration. If something is more concentrated than the other, it's going to react more strongly for the most part, unless the bond strength is different, which is our acid-base strength. There's kind of two factors when we're looking at reactivity: strong or weak, concentrated or dilute. These two substances, both of these acids have the same concentration, 1 molar, but we know acetic acid is weak, and so it does not react as strongly with that zinc metal. Get less hydrogen gas produced. If you're in class, we'd write a balance equation for this. Anyway, cool. And we know we've got a list of strongs. We memorized our strong acids and our strong bases. These are the ones that dissociate 100% of the time. Quick note, because you guys are smart. Worth noting that our sulfuric acid is only 100% for the first H. So this will give off 2 H's. It's called diprotic. It's a diprotic acid. The first H comes off completely. The second one doesn't. The second one stays stuck, and we'll look at kind of that value here in a little bit, but worth noting that as we're looking at our reactions. We say weak acids and bases dissociate less than 5% of the time, and that's where we've left it. That's where we've always left it, because we didn't know about equilibrium, because it is in equilibrium. You reach a point where all of the acids that are gonna split have split apart, but that doesn't mean they don't stop. We reach a point where for every acid that does split, one of our conjugate bases and the H plus go back, and we get this opposite but equal dynamic equilibrium established. And so we can actually show this. We can write what's called a Ka or a Kb. Ka is just equilibrium acid constant. Kb is a base equilibrium constant. But it's the same thing. Remember, we do not include our water because it's a pure liquid, but it's still products over reactants. The same K we've been doing all for our whole last unit. It's just now we're looking specifically at our acids and our bases. And so we've got products over reactants. We can solve for a Ka, or vice versa, solve back if we knew what that Ka or Kb was, if there's like a big appendices that told us. But K still tells us the same thing. It tells us the strength of the acid. If K is big, if K is larger, that means it wants to split to make lots of acid particles in solution, strong acids. If K is little, if it's less than 1, that means it stays mostly on the reactant side. It still tells us the same information. And now we have a tool where we can go, okay, here's 2 Kas. Which one's bigger? That's a stronger acid than the one with the smaller Ka, which is really nice. Again, just a tool to tell us how reactive is the species. And then we can shift it. If we know our Ks, we can shift them. Les Chatelet, more on that to come in a little bit. But that's why we've got our Kas and Kbs. Tells us their strength, the relative reactivities. Cool. Just a reminder, strong acids dissociate completely, full arrow to the forward, goes all the way. But our weak do not. We would say that they have a lower or less than 1 value. And that's where we get the double arrows. So it becomes important whether it is product favored, completely dissociate, or if we reach an equilibrium. And so we can just write this as a Ka. This is a generic form. Ha just represents any weak acid. A minus is the conjugate anion that is released when it dissociates into water. But this is the generic form for this. And you can start to plug stuff in and solve. The stronger the acid, the more H3O plus in solution, the more numerator, the bigger Ka. Ta-da! If it's a weaker acid, you don't get as much hydronium in solution once you reach equilibrium, and you get a smaller Ka value. So again, it's just telling us the relative strength of our acid. Cool. So let's try one. So phenylacetic acid, which is this big old molecule, we can kind of abbreviate it, builds up in the blood of a person with phenylketonuria, biology, an inherited disorder that, if untreated, causes mental retardation and death. A study of this acid shows that the pH of this substance is 0.12 molar, has a pH, so there's a molarity. It's got a so the pH is 2.62, and we had an initial concentration of 0.12 molar. What is the Ka of phenylacetic acid? Oh, ice table. Shoot, heck yeah. We know how to do this. Am I going to be able to squeeze in here? I should be able to. Let's give it a shot. Let me boop. Bada boop, bada boop, bada beep, bada boop. Cool, let's try this one. Because we know we got our reaction here. I'm going to try it. Ooh, it's going to be tight. Initial change, equilibrium. Initially, we didn't really have any of these, right? Boop, boop. We don't care about the water because it's a pure liquid. It isn't really going to change. We know the initial concentration of our acid was 0.12 molar. And then we know one other piece of information. We know the pH. Well, what is pH? pH is the measure of how many hydronium actually split apart into our solution. Because we put the acid in the beaker, we let it sit, that all split apart, we stuck in our pH probe, and then we measured the pH. Remember, that actually measures the hydronium concentration. The H3O plus, negative log of our H3O plus, gets us to, sorry, I wrote this backwards, no. Gets us to our pH. So we can actually solve, eraser. If we know the pH, we can actually solve for the hydronium concentration. I think if we do 10 to the power negative pH, we get our hydronium. So we're going to do second function log, negative 2.62, which means our hydronium concentration, H3O plus, comes out to be, what do we get here? I got 0.00239. So 2.4 times 10 to the 123 -3 molar. Ha! And this is at equilibrium. Cool. So now we know 2.4 times 10 to the -3. Well, it started at 0. Here's how much it increased by 2.4 times 10 to the -3. Well, what's our ratio? It's 1 to 1. So this would also increase by a factor of 2.4 times 10 to the -3 for a total 2.4 times 10 to the -3. And if this is how much they have increased by, that is how much we have decreased. I'm going to put it 0.00. We got the -3, right? 0.0024. I'm leaving it in standard notation to just make it easier for my mathematics on that side. Cool. So 0.12 minus 0.0024 gives us 0.1176. Oh, okay. With decimal places 0.12. More on that to come. Cool. All right. Well, okay. I think we wanted to solve for a K, right? What would your K expression be here? For this one, our Ka would be our H3O plus concentration times our phenylacetate ion, PAC minus, all over. We don't care about the water, so our HPA concentration. Sorry, let me clean that up a little bit. PAC, sorry. Boop. I think we just got to plug in our numbers, right? We're going to have, looks like 2.4 times 10 to the -3 times 2.4 times 10 to the -3, which is just this quantity squared, right? When I plug that in for both these terms, divided by our 0.12, and we should get a K. We had 0.0024 power 2 divided by 0.12. I get a Ka for this acid of 4.8 times 10 to the negative fifth, way less than 1. It is a weak acid. We know the Ka. We know the relative strength of this acid, whether it is reactant or product favored. We now have a method for mathematically determining how strong or weak our substance may be. Cool. Bunch of examples that we're going to be working through here to make sure we're doing okay on these. I just want to give you a good example problem to be using for your resources.